Hi there, it's Z here, and welcome back to the fourth video in a series of videos that I've been making related to using the tools of linear programming to help optimize capital budgeting. If you just joined this from previous videos, then welcome back. But if you stumbled on this video, you might want to reverse and have a look at the prior videos to get a bit of a feel of what we've done so far. So in the last video, we looked at a slightly more complex scenario where we had contingent and mutually exclusive and dependent type projects, in addition to yearly capital constraints. Now, for this current scenario, I'm going to strip away some of these complexities related to paired up projects or mutually exclusive projects and focus solely on the aspect of start date flexibility. Now, we saw that already in the previous scenario where we had one project that could either start in year one or it could start in year two. Now, in this setup, we're going to assume that all 10 projects have the flexibility to start any year. And for simplicity's sake, rather than have a multi-year spend pattern, the idea is if you choose to do the project in year one, it will finish and all the money that's required will be spent in year one only. And from a benefit perspective, the benefits start to accrue in the same year that you've completed the project. Now, rather than an NPV, you'll see that I've called it benefit per year. And why I've done that is because this is a scenario where maybe the company that is doing this is cash tight, and they want to maximize the returns and cash flow over a very near term look ahead window, say 3 years. Now, what I mean by that is, let's take an example. So for the first row, if I choose to do the project in year one, I spend the money in year one, so I get 5 million in year one, and I get 2 million for 3 years worth because I completed it in year one. I get the benefit year two and year three and beyond. But because I am sort of short-term focused, I will only consider the benefits for a 3-year look ahead. So you see that it's 2 times 3 years. It comes up a bit less because I'm using a discount factor to bring the money back to present value terms. So if I put this as 0, you get 6. And that's the principle of how this current configuration is done. So if you're on year 2, you get 2 years worth of benefits. So that's about 4 million, but it comes out to 3.5 because of the discount factor again. And if you go beyond the 3 years, you don't get anything. You might argue that this is a bit short term, and that's right, because in this setup, you don't look at the life cycle NPV. If you had a project that had really great NPVs on a life cycle basis, but it doesn't provide you with immediate returns in the near term at the start, then you probably opt not to do that project. So you could say the short-term bias is baked into the model. You could, of course, extend this to go beyond just 3 years and look at a 5-year horizon. Having been in a large organization myself, I could see how something like this might happen because individual projects will run their own economics, but you still need a way of allocating and selecting projects from a long list. And usually, if you are cash strapped, then you start looking only at the very near term. So that's enough about the setup. Now, one way of solving this problem is going back to how we did it in scenario 3, where we just repeated each project for a different start period as a different line. We could do that, and that's in fact actually what I've already done here, where this is a table representation of um, this view, but done in what I've called a tabular list. So what this shows is each project. So project one is repeated for each of the years that it could take place in. And there is a checksum to make sure that only one of the years is selected, and the benefits are calculated with the discount factor taken into account. So you can see that for project one, if it's in year two, it's less than if it were done in year one. So it's the same thing as before. Bit more tedious to set up. Okay, if you have 10 line items, probably harder if you have 50 line items. You could write a VBA script to do it for you. But just moving forward, this is a table that takes information from this format and then dumps it back into this just for ease of viewing it. So it's a lot easier to sort of look at the problem when it's presented this way, but we're solving it using this. So I'm going to use the solver to address this particular formulation. So you can see we're maximizing the column for NPV, and we do that by changing column F, which is all the do it in that year or the other, and this column I has a checksum to make sure you only choose one year. So if I hit solve, you end up with a solution that takes maybe only a couple of seconds to crank out. And let's say OK. It's 54.6 and it's got this particular configuration. Now, like I said, it's okay to do it this way. Takes a bit of work to get it into this format. You could write a VBA script to translate it, but to reflect the problem in this more compact table format rather than the less columns but a lot more rows format that you saw here. So to do that, I use a if-then formula to calculate the sum NPV over the 3-year window, and I tried to run this using solver. So we're going to hit simplex, and so constraints are the same as before. We have constraints on capex where it's this, this, and this, and for the selected years, all 4 columns from year 1 to year 4 have been selected, and there is a checksum column that I've set so that it's always equal to 1, so that only 1 year is selected. Now hitting solve on this produces an error because it's going to come back with a message saying that the problem isn't linear. So I'm just going to let it run while I talk. And I thought that was a bit weird when I first saw this because I didn't understand why what should be a simple linear problem was being interpreted as non-linear. So what I did next was went back to Excel Solver and tried to force it to work anyway because Solver says that it has a solver engine that works for non-linear problems, and I tried to click solve. So I'm going to run this via a macro instead of running it through the native format, and that's because Excel Solver doesn't have a timer. It really should. So I'm going to hit run just so that we can measure the time it takes to solve the problem. So you see it produces a result, but also gives a bit of a warning saying that it found a solution, but it says this may not be the best solution. And that's also, oh, oops, we lost it. I saved an earlier version I had, so let me just stick it back in. So it producing a result that clearly wasn't optimum, and we know that you have a better solution. There is a better solution that exists because we've looked at it when we ran it in this particular form, and we had 54.6 with this configuration. So I couldn't quite figure out what was going on, and I started to look for other tools that I could use to try and solve this particular problem. And online, I found something called OpenSolver, which is another add-in that's not part of basic Excel. But if you put this into Excel, what it does is it gives you access to many different additional features and solvers that you normally wouldn't have in Excel. So I'll step back and look at a simpler model just to explain how that works. So uh, OpenSolver is nice because it pulls in all the model parameters that you've built using Excel Solver. And if you hit Save Model, you can see it highlights the cells that are decision variables, the objective function with direction of whether it's max or min, and also the constraints. And there are a whole bunch of different solving engines that you can use, where instead of just simplex for linear, you've got a different um, a number of sets of linear and also non-linear solvers. So I'm just going to use this one, demonstrate how it works, and it shouldn't take too long. And yeah, so it's produced a result, and it works almost the same way. So I was going to use this tool to see if it could perform better than Excel's native solver. So let me just make sure that I've set up the problem in the right way. So yeah, column M, same conditions, I hit close, and in the solver, I'm going to choose a nonlinear solver engine, and I've chosen BondMin just to try it out. And I'm going to hit solve. And just like before, even OpenSolver doesn't have a timer, so I had to write a macro script to do that. So we're going to run it with the macro. So shouldn't take too long. Let me just pause. Oh, okay. 5 seconds. Uh, that's weird. It's coming up with a 0. And the reason for that is I'm going to run it without the timer just to see whether it's got error messages, because the timer sort of kicks out the error message. And as you can see, it spat out an error because it says the non-linear parser doesn't like the formulas that are in the cell, and it has to do with the if functions because I looked at the help file. So um, the next column over that I didn't explain is a reformulation of the same equation, but instead of using equals 1 here, I use more than 0. It's actually equivalent because the number can only go as high as 1, so they actually mean the same thing and the numbers come out the same. So just to show, exactly the same, but for whatever reason, this allows uh, OpenSolver to work with the model better. So I'm going to change this to column N. I'm going to say close, and I'm going to try and solve it now. So I'll try one round before I do the timing just to make sure that it does run. And it does. So and it's pretty fast. It gave the answer of 16.76, which is better than what uh, the Excel solver had with the GRG, but not that much better. And it's also relatively fast. So you can see it only took a moment as opposed to 15 minutes that if you were to run it with the Excel GRG solver. Funny thing as well, if you actually run it multiple times, I'm doing that now. Let's see if it works. It seems to jump around a bit. So it goes from this particular setup where only 2 projects get selected and it's 16.76 to a different number. You can see now it's gotten higher, 47.6. Seems to be indicating that it's not a not a trivial formulation. So if you look at uh, some online searches, you can see that they've got different types of non-linear problems as well, and it could be that we've stumbled on a non-convex representation of the problem. And the challenge with non-convex problems is that you may have multiple feasible regions and local optimum points. So it's difficult to find the best ever solution because you might only be stumbling on a locally optimum solution. So that's said and done. We're just going to give it maybe one more whirl and see what happens. So this time I'm going to time it so at least we can see. So run with timer. Yeah, let's do that. It's about 5 seconds, 2 seconds. So it's coming back to 5.31. That's not so good. Let's just keep on going. So it seems that that 47 point something number seemed to be the best so far. Maybe we'll get better. So as it's doing that, what is different for nonlinear solving is that the initial conditions matter. So in a linear programming sense, the initial conditions don't matter because they always get converge on one solution. But here, if you're starting from a different point, because there are multiple optimum points that are present depending on where you are, it does matter. So I'll give it one more try and then we'll see what happens. So 23. The good news is it doesn't take that long for it to crank the handle and run. So try one more. So it looked like that number of 40 something something was the best. But we seem to have gotten 50.04. I think this one might be the best because I've messed around with this a few times and I remember the number being somewhere around there. So it's not really a foolproof solution, and I started to try and look at using programming in Python to do this rather than running this solely on Excel. Now, a problem I discovered is that I couldn't do it using PulP because PulP is LP, linear programming only, so it doesn't accommodate non-linear programming. So I had to find a different library called Pyomo, which is a more professional, well, I wouldn't say professional, it's a more uh, heavy duty optimization library for Python that can incorporate non-linear problems. So uh, I went and learned this, how to use this, and here we've got an example that I'm going to just clear this and then run this together with you. So restart, clear all inputs. Yeah, let's do that. So the steps are similar to what you would do for PulP anyway. So here I'm importing the data uh, and loading it up. And that's what it looks like. And what the library, and we're gonna grab the information that we need and put it into a dictionary because Pyomo prefers to read dictionaries. Just to check, see, yep, the numbers came out, and these numbers basically, this numbers represented now in the dictionary, and I am instantiating a model, and it's called concrete model because Pyomo has one feature that uh, PulP doesn't have. It allows you to create models either as abstract or as concrete models. Concrete model means that the numbers are passed in at the same time when you build the model, whereas an abstract model is one where you can build the model without specifying any numerical figures and then feed the information later. Back to this. So I've done instantiated a model. I need to declare the uh, decision variables. You can ignore this. This is just a script that I wrote to initialize the numbers at random input, but I'm not going to use it here. Now, the nice thing about Pyomo is it took some digging, but I found a way to do if uh, expressions. So I initially started with something else that I've now commented out, but I found a way of doing it where you can express your objective using if statements. So I've done it here. I'm going to run this, skip over these bits. We're setting the constraints. And these are the constraints for the individual capex per year. And this is just a checksum to make sure that the value can only take one of the 4 years. And I'm going to be using bondmin as well, just to sort of compare it to Excel. And I'm going to click run. It's taken a bit of time. So I'm going to pause the video and come back when it's done. We're back, and you can see it took 3 minutes and 42 seconds. So 4 minutes is still a lot quicker than the 15 plus minutes that Excel solver took. Let's have a look at what the results look like before we are too quick to say that it's better. So it's a bit difficult to read the output in its raw form, but basically these are year 1, year 2, year 3, year 4. Now, I've got some script that's similar to what I did with PulP, where I'm just sort of cleaning up the data and writing it to a data frame so it's easier to digest and read. So let me just do that, and we can see what it looks like. So it looks like it's got some, so it's better than what we had earlier, in the sense that it's not just one project for those 3 years. So it's got a bit of a mix, and it's got 53.7, and it's within the limits. It's let's compare it to that 50.04. So 53.7 is quite similar to the 54.6 that we had when we ran it as a very simple linear program. Somehow, Pyomo must know how to reject the local maximums that don't look right. Some where, you know, if I were to run it using OpenSolver, maybe we'll get there, but it involves multiple clicking. So in that sense, it seems like using Pyomo with Python has given a pretty good result. And I'm going to transfer these numbers over to Excel. Let me just do that. And I've done that here. So 53.71, 53.7, and it's this configuration, kind of close to that 54.6. Now, after doing all that, I tried to have a closer look at the equation. So I know that the if was causing the solving algorithms, and it doesn't matter whether it was in PulP or Pyomo or in Excel, the if function does something really weird to the problem formulation. So I tried to see if I could do away with the if completely, and I realized, to my horror, that actually I was maybe overcomplicating the problem too much, because there is a way that you can rewrite the if conditions without the use of an if at all. So what you see in column O is it's the same number as the other two columns, but it's now written without the use of any ifs at all. And if you do it that way, and now I'm going to change the cell that we're focusing on. So instead of N, we're going to look at O, and I'm going to say close. And now we are focusing on this one, which is the sum of a bunch of cells that have no if function at all. It solves it really, really quickly. So I'm going to hit solve, and I'm going to hit simplex. So it's not going to, it doesn't give a error message like it did earlier. We're waiting for it to fire up. And you can see it's got 54.6, which is actually the same answer that you would have gotten if you did it the other way. And yeah, the TLDR version of this is please be very mindful when you're building any optimization model where you're trying to use if-then statements, because there may be a way that you can reformulate your conditions so that you maybe use binary variables or some other trick to simplify how the numbers are expressed, because doing that saves you a lot of time. So what you saw a moment ago was the running this on a linear solver, and the amount of time that it took was so much shorter. And let me just show you via the timer. So run solver with timer. So I've blanked it all out just so that it starts from the same point as it did if you were to use the other method. You can see it 10 seconds and you get the answer, and you're guaranteed that it is the best answer because it's a simple version of the problem. So we needed that time as short as possible because in the next scenario we're going to start doing multiple iterations of the same problem, and I'll explain why in a moment. So this has been a bit of a detour, but a useful one because I think I've definitely learned a lesson here. Right, see you in the next video.